My name is Jean-Louis Briaud. I'm a distinguished professor at Texas A&M University and the holder of the Spencer J. Buchanan Chair in the Zachry Department of Civil and Environmental Engineering. This year, I'm also the president of the American Society of Civil Engineers. So if you're a member, thank you, and please continue. If you're not yet a member, please become a member. I can assure you that it's a very good deal. If you do not think so, please drop me a note so we can have a good visit. If you're a student member of ASCE, make sure you transition to associate member when you graduate. Only 17% of you do that, and I really wish to increase that number significantly. Welcome to the 28th Buchanan Lecture. This year's lecture is again sponsored by Fugro. Anwar, Akhtar, and Fugro continue to support our activities, and we very much appreciate that support. Thanks to Fugro, and thanks to the contributors to the Buchanan Chair, the Buchanan Lecture continues to be free of charge for all participants. I also want to recognize those who have sponsored graduate fellowship in geotechnical engineering. Todd Soboda, Patrick Beecher, and the Terracon Fellowship, Willie Bowman, his wife Mildred, and the Bowman Fellowship, Alan Young, who created the Donmer Fellowship, Mark Balus and the Balus Fellowship, ECS with Mark Zortman and the ECS Fellowship, and the 3 Darrell Hooper Fellowships. We would like to continue to raise more funds for fellowship to support our geotechnical graduate students. These funds go a long way to help them. For example, a competitive fellowship of $1,000 allows an international student to get in-state tuition, which lowers their costs by some $6,000 annually. So your $1,000 gift has a 7-fold return and a tremendous impact on their lives. I also want to acknowledge another special group, and that is the board of CERGEP, the Consortium for Education and Research in Geoengineering Practice. This group of companies funds research aimed at solving problems encountered in practice. CERGEP now has 13 member companies, and I want to thank them for their proactive impact on practice-oriented research. The chair of the board of CERGEP is Shilandra Engle with Initech, and the vice chair is Todd Soboda with Terracon. Besides Initech PSI and Terracon, the companies member of CERGEP are A.H. Beck with Tracy Bretman, ECS with Mark Zortman, Fugro with Anwar Akhtar, Goron Dona with Ken Reiner, Tolune Wong with Daniel Wong, Reinforced Earth with David Hutchinson, Minar with Jonathan Dwight, Paradigm with Ray Meyer, Rabba Kistner with Gary Rabba, Aviles Engineering with Wilbur Wong, and Geosyntech with Rodolfo Sancio. If you wish to join CERGEP, please talk to me or Shilandra or any CERGEP member. I also want to recognize Blake Thurman, my assistant, who has been working long hours to help me organize this lecture. Thank you, Blake. Now for the program. First of all, this is an unusual year with this darn virus that is so disruptive. This is the first time that we offer the Buchanan Lecture online, and it actually has some advantages. Indeed, people throughout the world can now attend the lecture. We even have a group listening from Khartoum, the capital city of Sudan, that I visited some 13 years ago. Note that the Buchanan booklet is posted on the Buchanan Lecture website. We're also video recording this event, and we'll post a video on the Buchanan website within the next few days. We will also give the video to the Geo-Institute of ASCE, as we've done before, for them to upload on their site, along with the 27 other videos going back to 1993. Our first speaker will be Professor Lidija Zdravković from Imperial College in London. She will deliver the 28th Buchanan Lecture, which is about 1 hour. And we will not have any questions in this setting. Our second speaker will be Professor Idriss, formerly with the University of California at Davis. He will deliver his 2019 Terzaghi lecture, which is also about 1 hour. The event will conclude after his lecture. As you may recall, we would take a photo all together at the end of the event and then go to my house for a nice evening. This time, this will not be possible, but with your permission, I will still go home and celebrate, but all by myself. Now it is my pleasure to introduce Professor Lidia Zdravković. Lidia Zdravković, and that's Zdravkovic. And I thought Briaud was tough. So Lidia is Professor of Computational Geomechanics and head of the Geotechnics division at Imperial College London in the United Kingdom. She holds 2 master degrees from the University of Belgrade in Serbia. Let me open a parenthesis here. You see, some of you know that I play a fair amount of tennis, and Novak Djokovic is #1 player in the world in tennis, and he's also from Serbia. So I'm hoping that Lidia can introduce me to Novak and tell him that I'm looking for a good partner for the next couple of weeks or so. Just kidding. She also holds a Ph.D. from Imperial College in London. She joined Imperial College academic staff in 1999 and was promoted to full professor in 2013. Lidia has led and managed several research projects in collaboration with industry and other academic groups, focusing on the development and application of numerical methods in geotechnical design and providing solutions to a wide range of geotechnical problems, including renewable energy, nuclear waste disposal, and infrastructure resilience. She's a core member and UK representative on the ISMG Technical Committee 103 for numerical analysis. She has authored and co-authored over 200 technical publications and receives prizes from the Institution of Civil Engineers and the British Geotechnical Association. She has served as an elected member on the D.GE Executive Committee and has consulted for industry on projects involving Heathrow extension tunnels, cross-rail deep excavations, offshore foundations, and infrastructure slopes in conjunction with the high-speed rail route in the United Kingdom. Her topic is soil characterization for advanced geotechnical design, parameter derivation. I'm happy to welcome the 28th Buchanan Lecturer, Professor Lidia Zdravković.
Well, thank you very much for this kind introduction, Professor Briaud, and good afternoon, ladies and gentlemen, and good evening also from London. It is just gone 7 o'clock in the evening here. The topic of my lecture today, soil characterization and parameter derivation, is going to be discussed in conjunction with advanced geotechnical design. And what I mean by this is application of numerical analysis in geotechnical design, where I will be looking at integration of the geotechnical input in formulating realistic numerical models. And when I look at what we need to do in reality, which is here described here in the top line as having a geotechnical problem, having some ground investigation, and having a design brief. What we are trying to idealize in all these 3 situations is, first of all, perhaps deal with geometry of the problem and discretization in some way of the soil domain. Interpret the soil behavior from the ground investigation and think about suitable constitutive models that can be used for a given problem. And then design brief would tell us whether we are excavating or constructing something, or dewatering or loading, in order to decide on what are the appropriate boundary conditions to apply in the analysis. So each of these three parts form input to what I have globally here named a numerical solver, which then helps us get some predictions of what the ground movements, soil deformations, and soil stresses may be. And my lecture today will focus in particular on this right-hand side grouping, looking at ground investigation, integrating experimental evidence to characterize the soil behavior, and then select some constitutive models for selection of boundary value problems that I'm going to look at. So I will focus on the finite element method of analysis, defining initial ground conditions for the problem, characterizing soil behavior, and selecting and calibrating appropriate soil models. And my examples this time are going to focus only on clays, unfortunately, stiff clays. I will have separated these problems on those that can be analyzed as undrained problems with effective stress approach, but non-coupled analysis, and transient problems that require a coupled analysis. And all of the analysis that I will describe here tonight are produced by the finite element code ICFEP that we develop at Imperial College. So starting with undrained problems in stiff clays, I will focus here on laterally loaded monopiles for wind turbines. And the objective here is to look at the efficiency of foundation design and how this can be improved. And we are all very well aware of current codified design approaches that for laterally loaded monopiles that are based on a Winkler type beam spring approach, where the soil reaction to the predominantly horizontal loading of a monopile is usually assumed to be only provided by the lateral horizontal components of the stresses around the pile, and described with a PY relationship where the P represents a spring force and Y represents a displacement down the pile. And this approach has been developed from field tests on very slender piles with high L/D ratios. And as we move to offshore wind turbines, the monopiles here are much larger in diameter, up to 10 or more meters, but the L/D ratio is much smaller. So these are usually quite rigid responses in terms of ground movements. And even if we perform a finite element analysis without doing any testing, it is very clear from the vectors of ground movement drawn here around the pile that has, in this case, a 10-meter diameter and 20-meter length. It is very clear that the soil is responding not only with the lateral stress, but it is developing some shear stresses down the pile. And as the diameter is very large, there is quite large components of base shear and base moment in sort of counteracting the load at the top of the pile that has a horizontal force component and the bending moment. So what we have done here is to set off and try to derive a more accurate backbone behavior in terms of the horizontal force, horizontal displacement, pile response through numerical analysis. And this work was part of a particular considerations in terms of the monopile response, recognizing that we need to reproduce very accurately the operational loads where the small strain soil behavior may dominate, as well as conditions at failure where a storm load may cause a failure and loss of capacity of the foundation soil. So the whole project here was part of a joint industry PISA project, PISA standing for Pile Soil Analysis rather than for the Leaning Tower of Pisa in Italy. And it was recognized from the start that performing field testing of these large monopiles was not practical, and therefore an approach based on 3D finite element modeling helped with more small-scale pile testing in the field would be the way to perhaps get some more accurate design methods for laterally loaded monopiles. And the first objective here was to develop site-specific 3D finite element analysis capable of predicting accurately field tests performed at selected sites. And important to emphasize here that these analyses were performed before the field testing. So they were blind analysis performed as one would do it in design, whereas field tests here were of the medium scale piles with the diameters of 0.76 to 2 meters, maximum length of the piles 10.5 meters, and L/D ratios 3 to 10. And the principal difference with perhaps previous lateral testing of piles was that the load was applied at elevation above the ground surface, and here uniformly for all piles that was 10 meters. So if this first objective was then satisfactory and we have managed to develop appropriate 3D modeling of these piles and show that subsequently by comparing the predictions with field measurements, our next objective was then to go on and develop full 3D FE analysis of full-scale monopiles, and from there develop a new design methods. So the site chosen for testing the field monopiles for the PISA project was a stiff clay site at Cowden in the UK, located here in the northeast part of the UK, being a glacial clay site, representative of many of the sectors of the North Sea nearby. The sketch here on the right hand side represents the local area at the Cowden site, and it is important to identify here a previous test area that was a testing bed for a British research establishment for about 20 years, and this was a very good source of historic data on the soil behavior in this area. Pisa test site was nearby in the vicinity of this test area, but it was a fresh site that hasn't been tested before. And the diagram underneath shows the field testing that was done on site, comprising CPT experiments taken at the locations of the monopiles, of the future field piles, the boreholes from which rotary core samples were taken for testing in the laboratory, and then a trial pit here from which the block samples were taken also for testing in the laboratory. So trying to characterize first the site conditions for Cowden clay till. The CPT tests here throughout the site have shown fairly consistent ground profile, characterized by here some spikes that were a result of the material being a glacial clay with quite a bit of stone inclusion within a clay matrix. So these spikes here are purely a result of a tip of the cone hitting a stone. And then identifying here a sand layer at depth of 12 meters, which was also consistent with the previous site investigations, and that decided the maximum depth of pile test of field testing to 10.5 meters to avoid any interaction with the sand layer. Very negligible variability otherwise across the Pisa test site. So looking at the initial stresses in the crowd and ground profile, this profile here is derived from the historic data, going down to 40-meter depth and underlaid by the chalk, consisting predominantly of various grades of till, of grades of weathering of this till material, and our interest is really in these top 2 layers before we come to the sand. What we see in the first instance are some historic measurements of pore pressure distribution on site, and then some new measurements from the Pisa project, indicating that this top part of the deposit may not have a hydrostatic pore water pressure profile. And looking at other experimental evidence on the site, this is possible to happen, this so-called under-drain pore water pressure profile, if the permeability on site is significantly reducing with depth, which was the case, again, from the historic data of field permeability. And equally, if there is a lower aquifer for which the phreatic surface is lower than the existing groundwater level, and that also existing on the site. So our judgment was that we really ought to reproduce this under-drain pore pressure profile in our analysis, as that would clearly affect the effective stresses in the vicinity here where the base of most of the piles is ending, as that would affect the soil reactions along the base. So pore water pressure profile and the bulk unit weight estimated from about 21 kilonewtons per meter cube enable us to establish the vertical effective stress in the ground. And then we obviously need to understand what are the horizontal stresses in the ground, considering that this is an over-consolidated material. We have only historic data here, and this data is a bit questionable, indicating in these top 5 meters of the deposit very high K0 values, being pretty much similar to passive earth pressure coefficients. And so understanding that these data are obtained from odometer compression and swelling tests, that sort of type of testing is not quite representative of what has happened to this site in its geological history, because the site is highly glaciated, there was lots of horizontal shearing, and this top deposit is quite weathered with subvertical fissures. So it is very unlikely that the horizontal stresses can be this high. And thankfully, some recent experimental studies at the research group at Imperial have concluded that the K0 values in deposit like this cannot be more than 1.5 to 1.8. So we have cut the pore pressure, the K0 profile to 1.5 in the top deposit, but let it then follow the measured data for the rest of the deposit. So some level of engineering judgment, looking at all the data and understanding where it comes from, and then making a decision of what the adopted profile should be. Looking then on further to characterize now the mechanical behavior of the material itself, starting with the drain shear strength. and showing here normalized effective stress parts for this material from the PhD work of Emil Ushev, which was part of the PISA project. Normalization here is performed with respect to the mean effective stress at the start of shearing of each of the stress parts presented here. So this is a low plasticity material with a plasticity index of 18. And interestingly, the effective stress parts are showing very sort of ductile behavior and generally behavior similar to what would be expected from the critical state type material. And equally, looking at the deformed shape of a sample at failure, it is very clear barreling type of deformation without any clear shear planes developed in the sample. So summarizing on the right-hand side diagram here in a plot of deviatoric stress Q versus mean effective stress P dashed, the endpoints of these various tests, so the critical state stress points, achieved after the shearing in triaxial compression to about 30% of axial strain and to about 15% axial strain in triaxial extension. And adding the historic data, we have a very good agreement between the two sets of data, and also the historic data so extends the envelope because obviously those tests were done at much larger depths as well, whereas the PISA testing was constrained to those top 10 meters. So we can derive from here fairly confidently the angle of shearing resistance in compression of about 27 degrees and in triaxial extension of about 32 degrees. And this will have some implications later on for constitutive modeling as to what to do with a yield surface in the deviatoric plane. But for now, we have this strength. Considering that this clay is of low permeability, so order of magnitude 10 to minus 10 meters per second, our analyses are therefore likely to be undrained, laterally loaded monopiles under undrained conditions. So we also need to characterize here the undrained shear strength of this material. And we have, again, a good volume of historic data that here on this diagram shows quite a bit of scatter. So we are plotting an undrained strength versus depth. And so looking at how this data was obtained, the reference here of Powell and Butcher implies that these were pushed in tin-walled samplers. Some of these also hammered in, as we read in the reference. So there is quite a bit of sample disturbance that is also recognized in the reference when describing this historic data. And more importantly, there is sort of practically no characterization of this superficial depth of about a couple of meters, which would be quite important for laterally loaded monopile as the first point of resistance in terms of the soil reaction. So we needed some additional testing here for as part of the PISA project, and this was part again of Emil Ushev's PhD work. So we have some triaxial testing now conducted here on GeoBore-S rotary core samples taken from several boreholes, as well as on some of the block samples. And these tests perform on both 100 millimeter diameter samples and 38 millimeter diameter samples, and perhaps surprisingly showing fairly good correlation between the measured undrained strength and indicating that the behavior of the material is dominated by the clay matrix and not by the stone inclusion. Additionally, from the trial pit, we have done some hand shear vein testing, so that has characterized a bit more this superficial part of the deposit. And then, as we have them, the CPT traces were also interpreted in terms of Andrean shear strength correlations. And all of this gave a fairly confident picture of what the sort of interpreted undrained shear strength profile in triaxial compression may be, and that is this blue profile derived here. So again, important thing here, looking at all the experimental evidence, understanding the origin of the data and how much to trust that data, and then deriving the final profile of undrained strength. So having derived the strength parameters, we obviously need to understand the shear stiffness behavior and shear stiffness degradation. So what we have here are, first of all, field measurements. We have some seismic cone penetration testing that was not many tests were done, but the two that were performed were fairly consistent in terms of the G0 profile. And then we have our other dynamic shear stiffness measurements in the laboratory through Bender element sets of instrumentation installed both for vertical shear measurement and horizontal shear measurement, shear stiffness measurement. And these two indicated, again, a fairly consistent agreement with the field measurements, which gave us confidence that perhaps we didn't have any significant sample disturbance in rotary core samples, and also not very significant shear stiffness anisotropy, considering that GVH and GHH here are not that different. And there was also a historic geophysics downhole measurement that agreed reasonably well with the rest of the dynamic measurements here. And in addition to this, our triaxial samples were equipped with local strain measurements that showed, again, very good consistency between the shear stiffnesses in triaxial compression and extension at different stress levels, but quite distinctly lower than the dynamic measurements. And this, without at that time no other experimental evidence, this could have been attributed to perhaps insufficient resolution of local instruments to agree better with the dynamic measurements. So our judgment here was to essentially err on the side of the dynamic measurements and interpret the G0 profile as an isotropic shear stiffness profile with a multiplier of 1100 to the mean effective stress that is varying with depth. And having anchored that profile, then we go along and interpret the shear stiffness degradation from the triaxial tests in compression and extension. And what we adopt then as a final stiffness degradation curve is one that is perhaps degrading more rapidly than what the measurements here show, because what we have here is most of the triaxial tests are starting with the initial stiffness smaller than the adopted G0 profile. So what we want to achieve is some average stiffness here that agrees at medium strain levels with the average measurements from triaxial degradations and going then to large strains. So again, quite a bit of engineering judgment, looking not at just at reproducing the maximum shear stiffness in isolation on its own and stiffness degradation in isolation on its own, but looking at all the data and making a judgment of where what the degradation should be. So with this interpretation of the soil behavior, we now go along and try to choose an appropriate constitutive model, which we already sort of had in mind from the start, because there has to be some consistency between the constitutive model and the data that we have at our disposal. And clearly, so what we need to be able to reproduce is the measured undrained shear strength, reproduce the very small shear stiffness, as well as stiffness degradation, be able to cover a range of over-consolidation ratios, because we are dealing with a material that is on the dry side of the critical, and then also incorporate a non-triaxial loading conditions in a sort of more accurate manner. And we have selected here a critical state framework because the material was clearly behaving in that manner. Extended modified chem clay model, because to account for all these additional characteristics. And this extension is one that we have implemented in the code that we are using here, and I will elaborate on it in a minute. So looking at undrained effective stress parts, they are sort of climbing to the critical state, but the modified chem clay ellipse on the dry side of the critical would be over predicting very much that mobilized shear stress. So what we are introducing here is a nonlinear Warslev surface that captures very well these effective undrained effective stress parts. The sort of elasticity of the original MCC formulation is also replaced here with a nonlinear small strain overlay that allows us to vary the shear stiffness both with a stress level and with deviatoric strain. And then this difference in the strength in triaxial compression, drain strength in triaxial compression and extension is something that we have to be now careful about, because the in the deviatoric plane, the modified chem clay model originally has a circular shape, and that circular shape now, if the stress state changes from triaxial compression towards triaxial extension in conjunction with the lotus angle theta, the circular envelope would predict quite an unrealistic variation of strength in the deviatoric plane. So starting from triaxial compression at 27 degrees, by the time we get to triaxial extension, the circle would actually be giving us 40 degrees of phi dash instead of 32 degrees. We could have adopted a more Coulomb envelope, a more Coulomb irregular hexagon in the deviatoric plane, which is an envelope of a constant phi dash. So that would be 27 degrees throughout, but that would be quite conservative. So we have adopted a more general shape of the Van Echelen envelope that, with a selection of parameters, allows us to reproduce either Lade-Duncan or Matsuoka-Nakai surfaces, which are more appropriate for the real soil behavior. And this then gives us a more accurate representation of how the soil strength may vary from triaxial compression to triaxial extension. We are now here correctly reproducing 32 degrees, and then in between the maximum of sort of 5 to 6 degrees difference from triaxial compression, as is usually measured for most clays. So with this selection of and adjustments of an existing constitutive model, we can now finalize our characterization of the ground conditions, because modified chem clay model has a nice characteristic that the undrained strength actually is represented there with a closed form, in a closed form, depending on the initial vertical effective stress, depending on the K0 profile, depending on the compressibility and swelling lambda and kappa, and also on the overconsolidation ratio. So as we have so far derived the K-node profile that we want to use in the analysis, the undrained strength profile that we think is also representative of the ground profile. We can then derive the overconsolidation ratio profile from the existing characterization that we have performed and compare that with the data that we have obtained in the field. Again, these are historic data. And we are very satisfied here that the derived profile agrees very well with the measurements. So this gives confidence that we have essentially very consistently performed this calibration process and can now move to the analysis of the boundary value problem. And the boundary value problem is site-specific. So these are pile tests in Cowden. The discretization of the problem with 20 noded hexahedral elements in terms of the soil discretization. A pile is discretized with shell elements, 8 noded shell elements. And an important addition here to the whole domain discretization is the pile soil interface, which we have discretized with 16 noded zero thickness elements, which are modeled as elastoplastic because the lateral loading of a pile can produce a gapping around the pile, and we need that interface to be able to open and create a gap. And these gaps were very visible in the field tests that were performed subsequently. So we are performing an analysis by applying horizontal displacement at the pile top and getting the horizontal force as a reaction to those displacements. And as I said earlier, the analyses are undrained as the permeability of this material is very low. And I'm going very quickly straight away to comparison of the FE predictions with field measurements. And reminding you again that these field tests were performed after the event. So our initial predictions are blind predictions and representing here with this blue backbone curve in terms of the horizontal force and the ground line horizontal displacement. The ultimate nominal failure here is taken at horizontal displacement being 10% of pile diameter. And this jiggedy line here is a field test field test loading that had several stages of loading and rest period applied to essentially take away the effect of strain rates that are clearly visible at the beginning of the loading of each stage, because our analyses are not designed to model strain rate effects. That was not the objective of this project, and therefore these blue curves should be compared with these endpoints here, which represent the backbone curve without any strain rate effects. And added here for comparison is what the prediction that would be obtained by applying the PY methodology as codified in API DNV codes. Equally at operational loads, displacement of 0.1% of pile diameter. Again, very good agreement between the prediction and the measurements. And as a final result here, as I don't have time to go in all the all individual piles, is a bending moment in the embedded part of the pile, taken here for the shortest of the piles that were tested, L over D of 3. Again, a very good agreement of the predicted and interpreted bending moments from strain gauges and from fiber optics that were installed down the pile. So these comparisons demonstrated to industry partners and to independent review panel that numerical analysis, as we have performed it here, site-specific, carefully calibrated and modeled, can produce accurate and robust predictions that represent very well the field tests. And from then on, we have gone to other test sites and performed full-scale analysis, 3D analysis, over 100 analyses of pile diameters of 5 to 10 meters and L/D ratios 2 to 6 that are currently employed in development of wind farms. And then from each of those analyses extracted soil reactions from the nodes shown here in red from the pile soil boundary that were then parameterized to produce 4 soil reaction curves, so lateral load, distributed moment down the pile, base shear and base moment, and applied these in a simplified 1D beam spring approach, similar to the PY approach, but adding not just one soil reaction, but these additional 3 soil reaction components. So from a big complex and very specific 3D studies, the design approach is again 1D beam spring approach, retaining the simplicity, but with much improved accuracy. And this has been shown then in industry to significantly save on the foundation design, and it was rapidly taken up by industry, but in particular wind developers in the UK. And in 2017, the cost of wind energy with this more efficient foundation design was gone by half compared to 2015, and was even lower than the new nuclear. So the objective here was fully achieved by using the complex 3D numerical analysis that is fairly expensive to produce a design approach that is then applied, that is much cheaper, much faster, but is producing a more efficient and more accurate design. And I will just stay for a minute here for to talk still about undrained problems, but I will move to stiff plastic clays just to contrast their behavior compared to what we have seen with also stiff but less plastic clay. So this was the Cowden till that we've seen earlier, and we're now looking at London clay that has a plasticity index of 35 to 50%, and undrained stress, effective stress parts that start in a similar manner compared to Cowden stress parts, because the consolidation ratio is similar with London clay, but these effective stress parts are more inclined to the left, but equally they just reach the envelope and do not climb at all to critical states like Cowden envelopes, but they just curl up there and essentially stay there until failure. And this is clearly visible from the failed samples that develop very clear shear planes at failure. So the main characteristic now of this type of material that is different from the glacial clay that we've seen before is the strain softening of the effective stress parts, as well as shear stiffness and isotropy. And staying with the same boundary value problem as we had so far, the laterally loaded monopiles, we would need here a further extension of the modified chem clay framework developed for Cowden till to take account of strain softening and also to take account of shear stiffness and isotropy. Now, I will not now talk much about strain softening for this boundary value problem, because we have looked at this and showed that it essentially has a marginal effect on monopile capacity under undrained lateral loading, because there is no shear surface mobilized in the soil around the pile. However, the shear stiffness and isotropy is very important for operational loads, to be included in the calculations, as looking at all the data that we managed to summarize here from both commercial and research experiments, the shear stiffness, the maximum shear modulus in the vertical direction is much smaller than that in the horizontal direction, both in the normalized diagram here with respect to P dashed, and also in the unnormalized diagram for both the GVH and GHH. And more importantly, the two components of the vertical shear stiffness are the same practically for London clay, which is not necessarily the case for all plastic clays. And this ratio of anisotropy can be derived very clearly to about 2. The problem, however, then taking this from the elastic stiffness is into a shear stiffness degradation, because ideally we would need experiments like a hollow cylinder apparatus to give us this variation with strain independently of GVH and GHH. But if we have just a triaxial data, as we do have here for London clay, then we may be able to derive the GVH stiffness from the vertical Young's modulus interpreted from triaxial data, but we cannot really derive the GHH. So we have to assume some sort of scaling, and the scaling then has a question: if we start with a ratio of 2 at very small strains, does that ratio remain constant with further straining, or is it variable? And constitutive model selection here means that our small strain nonlinear model needs to be extended to account for this anisotropy, and we have done that here by adopting a 3-parameter model for transverse anisotropy of Graham and Hosby, which has parameters of anisotropy. So this is this parameter alpha. It needs GVH and needs the horizontal Poisson ratio, and then using elasticity, it gives us the relationship between GHH and GVH via the parameter alpha. So looking at what the prediction of some of these selected effective stress paths from the testing that we have used to interpret this shear stiffness. So this is a QP diagram and 3 stress paths at starting at 3 different stress levels. The dotted lines are the actual measured effective stress paths. If we adopt a constant ratio alpha here, it reproduces the right inclination of the effective stress path, but then it remains pretty much constant until we get to failure. And here, this being an overconsolidated clay, similar to Cowden clay, we have to adopt here a Washlev surface on the dry side. And this constant alpha ratio is practically just hitting the Washlev surface at a constant gradient. So to get the effective stress path, simulated effective stress path, to be closer to those measured, clearly this alpha ratio needs to be variable, and that variation is needs to be calibrated from the effective stress path. So it would give, in this case, a variation of starting with 2 at very small strains and down to 1 at about 1% of deviatoric strain. And this is then the parameter that we are going to take into the analysis of laterally loaded monopiles, having calibrated all other aspects of the extended modified chem clay, as we did for the Cowden study. So the only result that I'm showing here really wants to emphasize the need to account for anisotropy, as I said, at these operational loads. Performing an analysis here where we do account for anisotropy in GVH and GHH, we obtain the blue load displacement curve for a laterally loaded monopile, whereas if we perform an isotropic an analysis where we simulate stiffness in an isotropic manner, adopting either a GHH or GVH shear stiffness, clearly we get two different curves, and the difference is due to the magnitudes of the two stiffnesses, and clearly either one of these would be inappropriate or wrong in a sense at these operational loads. At ultimate conditions, the difference between the two is a lot more marginal and doesn't affect the ultimate conditions. So different type of stiff clays, plastic clay, very anisotropic, and in this boundary value problem, the strain softening of the peak strength of this material is not so influential, but the stiffness anisotropy is. So from that conclusion, I would then move to transient problems in the same stiff plastic clay, London clay, where I now want to demonstrate the importance of softening and that being taken into account. And here I will be looking at a different boundary value problem, which is a life cycle assessment of excavated infrastructure slopes. The behavior of these clays, as I said, is one that shows the softening from the peak strength to a residual strength over a certain magnitude of the shear strain. And this problem materialized in the 90s when, with the observations of some delayed failures in stiff London clay slopes. These slopes were constructed decades before, and suddenly they started to fail, causing obviously issues both along the motorways and railways, and it was so difficult to understand what was happening with these slopes by applying simple limit equilibrium calculations with which these slopes were designed to start with. So it was clear that some form of numerical analysis would have to be performed, and this was initially done by my colleagues at Imperial College, Professor Dave Potts and his research group, adopting in this case a simpler modeling framework, the strain softening more Coulomb model, because the dominance here was the strain softening of the material, but still using a nonlinear small strain overlay to simulate the shear stiffness degradation in the material. And the parameters of the strength for London clay are those of angle of shearing resistance at peak of 25 degrees and at residual strength of 13 degrees, so quite a big drop in strength. And what is happening here in the slope once it gets excavated is that the initial groundwater level, initial phreatic surface gets significantly depressed, developing some suctions above the newly created phreatic surface at the end of excavation. And then as the pore pressures go towards some steady state in the long term, this process is purely transient, and that transient process allows the soil strength to mobilize in some variable manner from the peak to residual, and therefore depending on the geometry of the slope and ground conditions, it can lead to failure. And these analyses clearly now have to be hydromechanically coupled. They cannot be just purely undrained or purely drained. And from such an analysis, this is an example of what was then discovered by doing such coupled analysis, is indeed that the soil strength is on the shear surface is developing from the toe of the slope, and the soil strength is initially some distance from the toe already at its residual value, which is judged also by the shear strains along the shear surface, and then some part of it is somewhere between residual and the peak strength, and then in the upper part of the slope maybe still at the peak strength. And this is a result of the analysis that is still stable, so just before failure, and in the next increment of the analysis all of this would just be completely progressing to failure. So in this case, for this geometry and conditions in the slope, the failure is happening 14.5 years after excavation. So these studies sort of demonstrated that the rate of softening was very important in the modeling, the slope of inclination and depth of the inclination of the slope and depth of the slope, the initial K0 profile, and the surface hydraulic boundary conditions on the excavated boundaries. And the conclusion was that for slopes in London clay, the maximum depth of 10 meters should not be, the gradient of the slope should not be steeper than 1 in 3 vertical to horizontal for them to remain stable. And these findings were then used subsequently for years in the redesign of such slopes for motorways widenings, as well as for the creation of new slopes. But today we are having again more infrastructure slopes being created and being constructed, in particular in conjunction with the high-speed rail project in the UK, that here is showing a connection from London to the north of England, or sorry, this is more central part of England, Birmingham, to be finished in the next decade, and then continuing until 2040, further extension to further north in England. These cut slopes are now much deeper, 20 meters deep, but also moving from London, they are coming in some geologically older clays. The design life is now required to be 120 years, and more importantly, the design here is concerned both with the stability of these slopes, but it's adding also another requirement because of the type of the rail track that is envisaged to be used. The base heave needs to be very limited, and the numbers that are floated for as limits over the period of 120 years are only about 10 to 20 millimeters of the maximum heave. So what we have started to look at here is, first of all, the implications of moving to more geologically older clays. And the big issue here is that they have much higher softening rates. And these results that I'm showing here are again from a recent study, in experimental studies at Imperial, led by my colleagues Matthew Coop and Richard Jardine, that have demonstrated that something like Oxford clay, for example, has a much more rapid softening compared to London clay. So the softening rates are much higher than what we have experienced with London clay. So what we have set to investigate here first is the rate of softening and its effect on stability. And we are remaining here with a small strain, nonlinear strain softening more Coulomb model with a small strain nonlinear overlay, and using non-local strain regularization to avoid mesh dependency because of the strain softening. And to demonstrate first the effect of the strain rates, what we have done here is to repeat the analysis for London clay softening rates, so calibrating the more Coulomb model as I showed on the previous slide with peak and residual strengths that are measured in the laboratory, and showing that indeed the shear surface starts to develop in a 10-meter deep slope, 1 in 3 gradient, but it stabilizes within the 10 years post-excavation and remains stable throughout the 120 years of running the analysis for that period of time. But the same slope with the same London clay ground conditions, but just changing the softening rate to that similar to Oxford clay, shows the failure of this slope after 21 years. So for ground investigation now, the important parameter to ascertain quite accurately is the rate of softening of these older clays. Further looking at stability, what we also set to investigate was the effect of shear stiffness and depth of excavation, considering that the studies in the 90s, after the studies in the 90s, we have now more recently had some significant engineering projects in London, from Heathrow Terminal 5 developments, Crossrail tunneling, Jubilee Line extension tunneling. So these 4 studies here are all sort of interpretations of the shear stiffness across London Basin, and they are interpretations of the isotropic shear stiffness of London clay, both from the research and commercial data. So what we set off to do is to look at these, both the previous depths of excavation that London clay was subjected to these new depths that these high-speed rail slopes are going to have, and applying the 4 different shear stiffness sets of parameters. And what these analyses have demonstrated is that the design line that was established in the 90s doesn't really move with respect to shear stiffness. We have also added here some analysis that I will explain in a minute that had to do with the bulk stiffness and with the permeability of the soil. But those 8 analyses for each of the gradients of the slopes and these depths that are up to 10-meter excavation really give completely stable slopes for 120 years. There is some so change and in the 15-meter deep slopes and gentler 1 to 4 gradient slopes, but anything that is deeper and steeper really fails within 10 years at the most. So the design line from the 90s remains the same. Some effect of the shear stiffness is seen for 15-meter deep gentle slopes, but anything that is deeper and steeper fails very quickly, even with this London clay softening rate, which is much lower than the softening rate of the older clays. So with this now, to give then the fuller picture to the designers in terms of the site investigation, we then move to assess this serviceability question and the base heave. And the first parameter here to look at is the bulk stiffness of the soil, because while the excavation is happening in an undrained manner, it is mainly governed by the shear stiffness of the soil. Bulk stiffness is not very active, but then the heave subsequent to excavation is completely volumetric, and that is going to be governed by the bulk modulus in the long term. And unfortunately, bulk stiffness is not a parameter that is usually interpreted from most site investigations. Fortunately here, we have a set of research data on London clay interpreted in the normalized bulk stiffness versus the volumetric strain. You can see here quite a bit of scatter in the data. And we're taking one of our previous parametric studies and interpreting a bulk stiffness with this black curve here, but recognizing that this nonlinear part of the curve will probably going to be mobilized very quickly after the excavation of the slope, and then the long-term heave over the design life of the slope will be governed by this tail end of the curve, which in this interpretation is K over P dash minimum of 40. And we can then easily, because within the scatter of the data, assume another degradation curve that would have a similar nonlinear part, but have a minimum tail end at 20 here, still within the data that we have, the scatter of the data that we have. And then the third curve that may be taking a bit higher tail end at 60, maybe as an upper bound of the experimental data. And what we get now as a prediction of the post-excavation base heave, so this is the boundary of the slope, and we're looking at this point here in the center of excavation, and on the horizontal axis is the time post-excavation in years. So this is our original analysis, and these are two derived analyses. Very clearly, the maximum, the amount of heave, maximum heave clearly depends on this tail end value of bulk modulus, being the smallest for the highest value of that minimum tail end bulk modulus. What is also interesting here is this affects the time to full heave. Again, the fastest with a higher bulk modulus, the slowest with a lower bulk modulus. And what we also looked here is the fact that the design envisages that the track will be placed perhaps a year after the excavation, expecting that most of the heave will happen during that year, and then the operational heave will be much smaller. However, in this case, we are seeing that the operational heave, the heave within this first year is similar for all these three curves, because probably that is happening during this non-linear phase of the degradation, but then the operational heave is quite substantial in all three analyses, and certainly much more than the 20 millimeters that the design, the track bed can sustain according to the design. So bulk stiffness, again, is now another parameter that the site investigation really should focus on. And finally, field permeability. So this being, again, as a volumetric deformation of the soil, field permeability is another important parameter. And here we are looking at a set of data that, again, is quite difficult to measure very consistently and accurately in the field, and the scatter is quite large, permeability with depth. The black line represents the permeability that we have used so far in all the analysis that I showed earlier, and we are adopting here a model for permeability that is dependent on the mean effective stress, K0 being this representative permeability at the ground surface, 2 10 to minus 9 for this black line, and then this is a higher permeability profile that still fits the field data, and this is a lower permeability profile that is still also within the experimental data. And looking again at the prediction of post-excavation base heave, now adopting the same bulk modulus, so the bulk modulus that has the tail end at 40, clearly the total heave will be the same because the bulk modulus is the same, but what is different is, again, the time to full heave. With a higher permeability, it will happen within 10 years, but with a lower permeability, the heave is completely mobilized more or less at the end of the design period of this design life of this slope. So it develops over all of the 120 years. And again, if we apply this boundary of 1 year post period before track placement, we see that the operational heave still remains very high, even if we have this quite larger permeability in the field. So again, field permeability is something, is now a parameter that needs to have perhaps a more attention in ground investigation if we're going to try to get more accurate predictions of what the likely heave may be in the long term. So summarizing this study of both the stability and base heave in London clay slopes, just repeating this diagram on the stability, where we concluded that design line is in agreement with lessons learned in 1990s. But if we are moving to older plastic clays that have higher softening rates, this design line is likely to move to the right. And therefore, the deeper and steeper slopes, unless some mitigation measures are applied, are not going to be possible with higher softening rates. Adding a similar diagram now for operational base heave, analyze here only for slopes that are stable. Obviously, no point analyzing heave in slopes that are going to fail. All 8 analyses here, so our original small strain stiffness data, and then these variabilities of permeability, field permeability, and bulk modulus, again indicate that unless the slopes are very shallow, then these very stringent constraints on what the maximum heave can be tolerated are not going to be met. And therefore, design will really need to consider some very probably expensive mitigating measures to reduce this heave to acceptable limits. And the site investigation before that probably should then concentrate on getting more accurate softening rates, bulk modulus, and field permeability, if any of these numbers can be reduced by better interpretation of these parameters. So in a very quick concluding remarks, hopefully I have managed to demonstrate that establishing a ground model from laboratory and field data is often challenging. The data can be disparate, and therefore all of the data needs to be looked at in a consistent manner rather than in isolation, so interpreting just single parameters and then trying to put them together, because in that way we may end up trying to simulate the soil that is actually not there in reality. Constitutive model selection is very much a function of available data and of design requirements. There's no point employing a complex constitutive model if we don't have the data to calibrate the advanced aspects of such a model. Hopefully, I have also managed to demonstrate that both of these processes require significant engineering judgment when deriving numerical input parameters, and also hopefully demonstrated that numerical analysis can be employed to inform the requirements from ground investigation, which essentially was the case of our involvement with high-speed rail and moving from what we have learned in the 90s and going forward into new soil types for these infrastructure slopes. So I thank you very much for your attention, and I apologize if I have overstepped my time.
No problem, no problem. Thank you very much, Professor Zdravković, for this remarkable lecture. You really took us from theory to practice in geotechnical engineering. Honestly, I used to think of you as a very theoretical person, but you've changed my mind. I particularly appreciated that while starting at the most fundamental level, you ended up with very practical predictions and explanations, including showing how much money you saved the industry. It's my pleasure to give you the 2020 Buchanan Lecture plaque. I do not have it with me here because it is already on its way to London, along with the honorarium check. Thank you again for a wonderful lecture.
Thank you very much. Thank you very much for your hospitality and for the invitation.
Most welcome. Now it is my pleasure to introduce Professor Izzat Idriss. Professor Idriss is Professor Emeritus of Civil Engineering at the University of California at Davis and an independent consulting geotechnical engineer currently residing in Santa Fe, New Mexico. His areas of teaching, research, and practice are geotechnical earthquake engineering, soil mechanics and foundation engineering, earth fill and rock fill dam engineering, and numerical modeling. He joined the faculty of the University of California at Davis in 1989, following 20 years at Woodward Clyde Consultants in San Francisco, Santa Ana, and Oakland, where he was a senior principal. He was a member of the teaching and research staff of the Geotechnical Engineering Group at the University of California at Berkeley from 1967 through 1975. He retired from the faculty position at University of California at Davis in July 2004. He's received many awards and honors over the past 50 years, including election to the U.S. National Academy of Engineering in 1989, receipt of the first Bolton Seed Medal from ASCE in 1995, the Distinguished Scholar Public Service Award from the University of California at Davis in 1999. He was elected an honorary member of the Japanese Geotechnical Society in 2005, was elected a distinguished member of ASCE in 2008, and is the recipient of the 2010 Ralph Peck Award from ASCE and the 2010 Casagrande Memorial Lecture from the Boston Society of Civil Engineers. He was elected an honorary member of the Earthquake Engineering Research Institute in 2012, and the recipient of the George Hausner Medal from EERI in 2018. He presented the Terzaghi Lecture in 2019. His topic is Response of Soil Sites During Earthquakes, a 60-year perspective. I'm happy to welcome the 2019 Terzaghi Lecturer, Professor Izzat Idriss.
Thank you very much. I've been so engrossed in listening to Professor Zdravković that it takes me time to get back into talking rather than listening. Let me see now. We got to share my screen. Hope you can see it now.
Yeah, you got it.
And let me get into the presentation mode.
Perfect.
And get the, where is the?
No, you got it. You're there.
But I'm trying to get the pointer.
I think the pointer is good.
Oh, here it is. Now I got it. This one is easier. Oh. Yeah. Well, thank you very much, and good afternoon to everyone. Good evening, wherever you are, or maybe morning. I have no idea where everybody is. But I'm glad to be here myself, and appreciate the opportunity to represent the Terzaghi Lecture, which I gave about 1.5 years back in Philadelphia. And what I chose to talk about was the response of soil sites during earthquakes. Take a look at what we've been doing for the last 60 or so years. And obviously, this is a Terzaghi lecture, and I'm extremely honored to have been selected to give this lecture in last year, following a tremendous number of highly talented and well-recognized individuals, all in honor of the late Professor Terzaghi, whose picture you see here. And he certainly is considered, and likely, rightly so, as the father of soil mechanics. What I'm going to talk about today are these topics. Why do we worry about site? Why do we consider site response? Then, because of site response is so dependent on what input we put in, we have to understand, and what output we get. So we have to understand what nature has told us by looking at recorded earthquake ground motions. And therefore develop models to estimate these ground motions for future applications. And therefore, I'll look a little bit about comparison of the empirical earthquake ground motion models and need for analytical approaches. And then I'll take a little time to look at the historical perspective, since we've been looking over 60 years, and look at what we have available to us, and give you some examples on how well we do or don't do, and then give some concluding remarks. So let's get started. Why site response? Well, I always like to show a few nice pictures, and this is the picture of the east span of the San Francisco-Oakland Bay Bridge. This is the artist rendition, actually. It's not the actual finished construction, but the bridge was completed finally in 2013. Now, I was involved with it from 1990 until 2013, so it's been quite an experience to be involved in such a beautiful project. And another thing that we also have to be concerned with are nuclear plants like this one in California, and high-rise buildings. And therefore, we need to decide what it is we're going to apply as an input to these variety of situations when we're doing an analysis. Now, typically what we begin with is having just a half space consisting of something very hard, so it doesn't change very much with depth or from location to location. And we call that an idealized outcrop. And we'll define whatever we record as point C, recorded this. So point C then would correspond to earthquake ground motion recorded on a rock outcrop. Then if we have a soil site, now point C is no longer here. What is really driving the soil site or soil profile is what's happening at point D. And what happens at point D is not the same as what happens at point C. And if we have a soil profile, what we measure, if we have no structures, and we call this a free field condition, is at what we measure at point A. So now we are looking at point C, which is a rock outcrop up in the rock exposed to air. Then at point D, which is still on rock, but overlain by a soil profile. And we're looking at point A, which is the free field with no structures, no dams, no bridges, no nothing, except the air above that and the soil profile. And now if we put a structure in this place, then we still have point D. That doesn't change by putting in the structure. We still have point A away from the structure on either side. We call that the free field. We still have the foundation soils, but now we have a structure, and we have to apply to that structure we have to calculate, I should say, whatever is happening within that structure. That's all driven by this point, what's happening at point D, which is dependent on what we find in point C. And fortunately, given the nature of whatever this profile is, we've evolved over the years, we've evolved procedures to modify what's happening at point C to get to D, and therefore drive the system and calculate what's happening in this structure. And of course, in geotechnical engineering, earth and embankment dams are very important, whether they are water dams or tailings dams or whatever system that we are looking at. And that's where we have now, instead of having a building like I showed earlier, we'll have an embankment over the foundation. We still have the free field to worry about. We have point C, which is not in this picture, but it's a hypothetical, as if there was nothing left here, but we only had the the half space exposed to air, and we'll have point C. Then we'll convert that to what's happening at point B, which will now be at this location here, and that will drive this system. And then we can calculate what's happening within this embankment and the foundation soils. So that's the process that we go through. Now, why do we need site response? We need site response so we can check what we've done when we run this analysis over here. Because we have lots and lots of recordings in the free field. We don't have that many recordings on dams that we, with full information, so we can recalibrate with respect to what's calculating on dams. Our structural friends have done a lot of analyses of the structures, and I think they've convinced us they can do a good job back figuring what's happening in the structures. But we geotechnical engineers, and I'll stick to embankment dams as our structure, so to speak. So then to respond to that question, why site response? A ground response analysis provides a means to check the results of the free field dynamic analyses that incorporate soil structure interaction, the picture of the structure I showed, or the dam sitting on top of the foundation, or soil foundation structure interactions, if we have piles or deep basement and what have you. Therefore, it's important to have in our computation tool bucket procedures and computer programs that we can rely on to provide us with reasonably reliable estimates that correlate well with measured values and are physically meaningful. That's a mouthful here. And the emphasis I want to make is on reasonably reliable estimates. I prefer to use the word estimates rather than prediction. I know a lot of people, a lot of my colleagues love to use that word, but that's not here or there. But reasonably reliable is really important. We don't know how accurate they will be, but they can be. We can rely on them. Whatever we calculate has uncertainty in it. We have to always be cognizant of that. But we want to be as reliable as we can be, but also we want to make sure that we are physically meaningful. And hopefully I'll be able to illustrate some of that as we go through. So now let's look at these earthquake ground motions and the earthquake ground motion data available to us. When I started back in the early 60s, there are about 10 recordings worldwide, 10 usable recordings, I should say. And let me show you what we have now. We've, over the last 15 or so years, we've gone through what's called the New Generation Attenuation Project, or the NGA project, which was initiated in 2004 and resulted in accumulating, checking, organizing, and disseminating tens of thousands of motions recorded during earthquake as follows. We have various regions that have different seismological settings, different attributes, and therefore we had to divide the world, so to speak. And we look at what we call shallow crustal earthquakes in active tectonic regions, like California, like Japan, like Chile. We call and that work is designated the NGA West, and that particular project was the NGA for the New Generation Attenuation. And since we are looking at the western part of North America, we called it West. And the reason for two is that the process was started in 2004, and West 1 was finished 2002. We added lots more data following that, and in 2014, NGA West 2 was completed. And of course, there are parts in the world which we have shallow crustal earthquakes in stable continental tectonic regions, such as the eastern part of the United States and Canada, and the central parts of the same two countries. And we call that NGA East. And then, of course, we have the subducting earthquakes at the intersection of various continental boundaries. And for that, we have had the NGA subduction project. The NGA West 2 was finished in 2014. The NGA East was finished about a year or so ago. And NGA subduction is being finished. There are 3 key models being developed, and 2 of which have already been published. The other third one is still in progress. So that the range of data has been collected to show you the extreme jump from 1964 or thereabouts when I first started in this. The 10 recordings now we have in NGA West, over 21,000 recordings, of which 19,572 are usable. And the range is huge. This M is for magnitude, the size of the earthquake, from magnitude 3 to 7.9. The R rupture is the distance from where the earthquake occurred to where we recorded it, from 1/10 of a kilometer to 1,500 kilometers. And this VS30, which we'll be hearing a lot today, it's the shear wave velocity averaged over the upper 30 meters, 100 feet. And it's not averaged by averaging the values of the shear wave velocities measured. It's averaged by averaging first the arrival times and then taking the inverse to get the value of the shear wave velocity. And the range is from 89 meters per second for the NGA West 2 to 2,100 meters per second. 89 represents a very soft site. 2,100 represents a very hard site, a rock site. And this is just a plot to show you where everything is in terms of magnitude and this rupture distance. And so the magnitude recorded during the cluster earthquakes, actually this is, but I'm only showing less than 500 kilometers and greater than magnitude 3. But you can see there's a huge number of recordings and various mechanisms. We don't want to go into those details. Now the NGA East, they're a little less than 10,000, about a little over 9,000 recordings, of which about 8,900 are usable. And the range now is only up to 5.85 magnitude, and the rupture distance from 4 to 3,500 kilometers. And this shear wave velocity VS30 is from 144 to 2,000. And the range looks something like this. You can see that the largest is magnitude 6. So we don't have many recordings at very large magnitude earthquakes in these stable regions like the eastern part of North America. The subduction earthquakes, there are 71,000 recordings, but the usable free field are only just shy of, just over 49,000 recordings from about 700 or so events. Now, when you look at a subduction earthquake, it's actually two parts to a subduction zone. The subduction is caused by one plate going on another plate. This happens to be in Central America. I just pulled it out as an example. The North American plates, the Cocoa plates, which is in Central America, subducting under the North American plate. And there are two parts here where earthquakes can occur. The shallower part, less than about 50 kilometers in depth, we call that the interplate and sometimes the interslab. And then the lower part, which is deeper than 50 or so kilometers, and we call that the intraslab. And the number of recordings then can be separated based on where the earthquake occurred. For the interface or interplate, the magnitude ranges from 4 to 9.1, and the rupture distance is from 8 to 6,500 kilometers. And this VS30 at a site at which these were recorded ranged from 53 to a little over 2,200 meters per second. The interslab, the deeper events, the maximum is a little smaller than the interface. Usually the largest events occur on the interplate or interface, like the Alaska earthquake in 1964, or the most recent Tohoku earthquake in Japan, which is a 9.1 shown in here. The interslab is up to about 8.4, I think this was in Chile in 2010, 12, something like that. And the rupture distance is shown in here, and so on and so forth. And this is all the recordings. And you can see this again, magnitude versus rupture distance, and up to the 9.1, which is from Japan. And you can see the huge number of events as we saw. And now, one area that dominates these is really Japan. It's quite a few from Chile and from Taiwan, but the real large number is from Japan. Cascadia, which is the northwest part of the United States, covering Northern California, Oregon, state of Washington, and then into the British Columbia region, there aren't that many recordings, so we are limited there, and we have to borrow from other parts of the world. So what can we learn from these recordings? These now, you had about 50,000 subduction, about 9,000 from the east, and about 19,000. So that's about 70, almost 80,000 recordings altogether. What can we learn from that? And the easier thing to look at is the spectra. And I hope everyone knows what a spectrum is. I'm not going to describe what it is, but I'm hoping out of the 170 or so individuals participating today, and I hope you're all enjoyed the first talk, and I hope you're enjoying this one. And so we look at these spectra, which for every recordings we can generate a spectrum. And then at each site, we record motions in 3 directions, 2 horizontal, which are usually orthogonal, like east-west or north-south. But they don't have to be east-west, north-west, but they always are orthogonal at 90 degrees to each other, and then a vertical component. And what we've concentrated our attention for the most part about the 2 horizontal component, and we calculate the spectrum that gives us the median values as we rotate the spectra. And this is, again, details that I don't want to go through right now. So that is the spectrum I'm going to talk about. So it's basically, it's very close to what you might call the geometric mean of the 2 spectra. If you calculate one horizontal spectrum, is called that H1. The other one is H2. Calculate the spectrum for H1 and the spectrum for H2, and you take the geometric mean of the 2, you get the number that we've been using over the last 15 or so years. And so the spectral shape is, and what I like to look at is, because the spectra will vary hugely in their amplitudes, and depending on the distance they're recorded at, the magnitude, the site conditions, and so on and so forth. So what we've developed over the years, and I think Professor Hausner, the late Professor Hausner at Caltech, started looking at that, what we call the spectral shape, whereby we take the spectral ordinate that we calculate at each period and divide it by the peak horizontal acceleration, or the acceleration at close to 0 period. So the process then is the spectral shape, the ratio of the spectral acceleration. And typically we use this acronym PSA, which stands for pseudo-spectral acceleration. At the period T, we divide that by the spectral acceleration at 1/100th of a second, which is 100 hertz in terms of frequency, which is a very stiff system, and therefore it's very close to the peak acceleration. And typically corresponds to the maximum acceleration of the record. So the value at t.001 is very close to PGA. And the things that I like to look at after creating this spectral shape is to look at the plot of that ratio PSA over PGA versus period. Then what is the value of that, the maximum value of that ratio, and at what period does that occur? So first we have a spectrum. This is a typical spectrum of recording from Loma Prieta, and I selected a rock site for 1,428 meters per second. And it's fairly large motions, about 0.45 G for the peak acceleration, and the spectrum goes to about 1.6 G. So it's a pretty significant spectrum. And then if we now to take each one of these, and that's the spectral value, again, PSA plotted against period T. So if we take any one value, let's take it 0.1 second, take this number divided by this, that will be that ratio I'm talking about. So we take this value divided by itself, this will become 1, and we'd have something that looks like this. So now we have 1, and then climbing up to this value, and that's the peak I'm talking about, and this is the period at which this peak occurs. For this particular record, the peak is about 3.6, and it occurs at about 0.4 seconds. So now let's examine what the data are telling us. So if we take a look at, I'll just look at NGA West 2 data. And we take that ratio, the period at which this occurs. Let's remind ourselves again. Now we're looking at when this period occurs for each spectrum that we have recorded. And for the NGA West, I'm looking here at magnitude 4 to about 7.9, and distance from 1 to 500 kilometers per second. But I'm concentrating only on really harder sites from 600 meters per second to 2100 meters per second. Basically, this becomes really, this is sort of a weak rock, and this is a much harder rock. The really hard rocks are in the 3,000–4,000 meters per second, but this is 2100 meters per second is still a hard rock. So I'm looking here only at rock sites and for these. And when we plot this period as a function of magnitude, we just see a scattergram and no dependence. When we plot it against distance, again, the same, this is the period at when the maximum occurs for the same data points, but versus distance, we do see a trend. Now this is log period. So these numbers are not as important as these numbers. This is 0.1, that's 1, that's 10 times this. So you gotta keep that in mind. So the trend in here, which was done actually by regression, is just shows that there is a tendency for this period to increase as distance increases beyond maybe about 20 or so, 20, 30 kilometers. Now we look at soft soil sites on the other end of the spectrum. We have the really hard sites from 600 to 2100 meters per second. And the softer sites, really soft sites, are about 90 to about 200 meters per second. And we look at the trend of this, where this period, the value of that period as a function of magnitude, and it looks something like this. There's a little bit of scattergram type of thing, no dependence up to about magnitude 5-ish, maybe 5.25. But then as the magnitude increases, there's the tendency to increase. But again, don't use your eye to split the difference. This is logarithmic, and this value is 1/10 of this value. So you be careful with that. When we look at the same recordings in terms of this period as a function of distance, again, we see a definite trend with distance, increasing with distance, again, from about maybe 15, 20 kilometers onward. So then we can, from that, we learn that at rock size, this value of Tmax is essentially independent of magnitude and VS, the average shear velocity, but increases with distance. For soft soil sites, it's essentially independent of shear velocity, but increases with magnitude and distance. So let's look now at that ratio, which is the maximum ratio that we see in the spectrum. Just to remind ourselves, we're looking at this number here. And when we look at both rock sites and soft soil sites, we see that as a function of magnitude, there is definitely no dependence on magnitude, but there's something very clear that the smallest number is well above above 2. In fact, this is a value of 2.5, and only very few values fall below that. In fact, about 97% of the data of the recordings fall above 2.5. When we look at that dependence as a function of shear wave velocity, again, we see no dependence. These are the soft soil sites, less than about 200 meters per second. These are the rock sites above 600 meters per second. There is no dependence on this, but of course, the lowest value is certainly 2.5 and above is about 97% of the recordings. When we look at the dependence as a function of distance, we don't see much of a dependence either, but either for rock sites or for soft soil sites. So then, concluding regarding this maximum ratio, the maximum ratio appears to be essentially independent of magnitude M or VS30. There is an apparent hint that this metric may increase with our rupture, but only a hint, not really. The range of this ratio is from 2 to about 6. This ratio exceeds 2.5 for about 97% of the recordings. These conclusions apply to rock as well as to soft soil sites. Oops, I got this wrong. Where am I? Ah. Okay, so now what have we, well, to repeat what I said at the beginning, is that what is the utility of looking at recorded data? I just want to reiterate that so that we don't forget why a geotechnical engineer should really understand these recordings as best as he or she can. Among the most important utility is to derive, calibrate, and verify earthquake ground motions models to obtain. We need that motion at point C. Remind ourselves what point C is. It's a half space consisting of very hard material above 600 meters per second shear wave velocity. It's not with no structure near it or above it. And that's the point C we want to start with. So we need to have those models that allow us to obtain these values, because we need to apply this value at point C to anything we're going to analyze, such as a soil foundation structure or an embankment foundation. And so these motions that at point C should be based on models for sites having a shear wave velocity greater than about 600 meters per second. So again, to remind ourselves that we're going to do the analysis for the soil, for the structure, the soil sitting on that half space where points we calculated. We obtained point C from these models, but now we're going to get point D to apply to the system to calculate the process. But in addition to that, we need the utility of the recorded data is to allow us to verify that we can calculate when we apply our analytical models, we can recreate what's happening in a free field in a reasonable way. So that it allows us to calculate the motions to use as a check on the results of point A. So that's the two-headed effect of this, of looking at these ground motion data. And I hope everyone who gets involved in looking at the effects of earthquake on soils and soil structures always keeps that in mind. We need the way to get the input from point C to point D and then on into the system as best as we can, and rely on recorded data to assist us in this, making that assessment. And we need what's happening at the free field like point A, so that when we do the analyses, we can go back and check on that. Now, I've been, as Professor Briaud mentioned, I've been at this for a long time, many of which were spent in private practice and for the last 30 or so years at the university and in consulting arena. And I've seen so many analyses and so many results where you ask the question after someone makes a huge presentation, did you make a comparison at this point and see what kind of numbers you're getting? And about more than 50%, I won't be nasty, more than 50%, they say no. And those that do have the numbers, they forgot to examine them. And then when you examine those numbers, at least about maybe 20, 30% don't make much sense. So please, anyone who wants to do this, make sure that first you make sure that you have any extent of your model away from the structure or a dam or whatever you're looking at is far enough to really be in the free field, not to be affected by what's happening in the structure. That's number one. Number two, to make sure you look at those results. And number three, to know enough to judge whether the results make sense or not. So now we'll move on to our next topic. And that's examining what these models that people have been working on. And again, I'll only look at the NGA West 2. And I won't go through the details because it'll take another hour to just examine all those, but I'll give you the bottom line. Conclusions regarding the use of empirical earthquake ground motion models can be summarized as follows. The spectral shapes obtained for a rock site, and I examined the 760 for this purpose, but I think it applies from 600 onward in a consistent way, because the USGS, the United States Geological Survey, uses the 760 as what they call the generic rock site. So for that particular site, they're using the NGA West 2 ground motion models are generally consistent with the recorded data. So I feel comfortable recommending that people can use these models to estimate what the motion at a point C will be to use to convert to what needs to be a D and then use it in whatever model they want to use to make the analysis. Now, from then on, it's up to the user to be sure the model is right. And as we heard in the last lecture, the properties are right, as we'll also examine a little later, and so on and so forth. But for soft soil sites, they are not as well constrained. So I think these models have done a very good job on rock sites. They've done actually a poor job on soft soil sites. And then it basically in between, from about 200 meters per second to 600 meters per second, it gets better and better as you get stiffer and stiffer. Because the nonlinear model that was incorporated, I think, is deficient, is my word to see. So I think we need to keep examining that, because we need those results to examine what we calculate at point A. At point A is typically not at 600 meters per second. The point A sometimes is at the 200 meters per second or so, but it's somewhere in between those two most of the time. So we need to be careful about that. But if you studied the ground motions as much as someone like me has done, you can still, even without a model, you can judge whether the results are looking reasonable or not. So at least it's up to, so, and these data are available. So anybody can download these, all the recorded data, what they call flat file models for all the data that I just mentioned, NGA West, NGA East, and when did I start, Professor Briaud, so I can keep track of my time?
About 30 minutes ago.
30 minutes ago. Did you say 20? Okay. So so different results were obtained to soft soil sites using other conclusions stated above were applied to each. Accordingly, it's appropriate to use the empirically derived earthquake ground motion models to estimate spectral values at a rock site, which becomes the rock outcrop for a specific application. Such spectra can then be used as the target spectrum at a rock outcrop in a seismic analysis. So let's look a little bit about this historical perspective. And now I'm going back to just about 60 years ago, the early 60s. But to instigate that, I need to go even farther back. So now I'm going to start going through a few of these slides to go through that. And we start out with the 1906 San Francisco earthquake. I think probably that was the first time the profession started looking at are there differences in what we're seeing? Why are we seeing differences in performance? And is it because of some local site conditions? So the performance of various sites during the 1906 earthquake highlighted the importance of site response during earthquakes, as is noted by Lawson in 1908. He wrote the report following that earthquake, emphasized the effects of local site conditions. Although some attempts were made to explain these effects using wave propagation theories, even at that time, it was not possible at that time to go beyond qualitative explanations. Then one of the most important names in this arena is this Professor Kanai in Japan, who from in the early 1950s, in 1952, Professor Kanai proposed the use of the continuous solution to the wave equation. So we go back to the use of wave equation to study side effects on earthquake ground motions. Professor Martin, who was teaching at the University of UCLA, University of California at Los Angeles, visited Professor Kanai in 1957-58, and he brought Kanai's work to the attention of US researchers and practitioners in 1958. But unfortunately, this was met with strong resistance from structural engineers in the USA. He said, "Didn't want to have, no, don't bother me with those kinds of details." But in the 1960s, then, when I was getting started, I started my research in 1964 with the late Professor Seed, who had a few years earlier presented a paper at the World Conference on Earthquake Engineering, advancing the concerns with the behavior of soils during earthquakes and the potential effect of local site conditions on earthquake ground motions. Donald Hudson, who was a professor at Caltech, and actually I took his courses on the theory of vibrations when I was a student there, proposed the use of values of damping that are dependent on the level of deformation in structural elements. That was in 1963. And shortly after that, Penzine, Parmalee, and Seed developed a bilinear procedure and wrote a computer program to calculate the response of soft soil sites in 1963. So that's what I had available to me when I started in 64 to build upon. Professor Martin, that's Jeff Martin, who at that time was a student at Berkeley at the same time I was a student at Berkeley. And he went back to New Zealand, where he was born and raised, to teach at Christchurch. And then came back to the United States some 20 years later or thereabouts. And then eventually taught at University of Southern California. But as part of his thesis, he suggested the need to incorporate the influence of the level of shaking in calculating response to burst dams. And that was happening at about the same time I was just starting, but he didn't carry it any further. It just sort of rang a bell in my head. So what I went through as part of my thesis was to examine some tests that had been done by Thiers and Seed and suggested, but based on those results, suggested the use of strain-compatible modulus and damping values in site response calculations, and came up with what we now call the equivalent linear procedure in 1966, and then eventually compared it to the bilinear solutions that strain-compatible modulus and damping values can be used in a linear program to produce comparable results, and therefore the birth of the equivalent linear solution, and that was in 1968. So basically it was myself and the late Professor Seed who developed that, and that's been basically the basis for all the analyses that we've been seeing over the last, that's not quite 60, about 55 years or so. And what is being done here is to say soils actually behave as shown in the left loop over here. This is a hysteric loop. As you increase the stress, you're increasing the strain, but if you reverse the loading, it'll go down And then if you reverse the loading again, you develop what we call a hysteretic loop. And the bilinear solution was to replace this nonlinear by a two linear line and called the bilinear solution. And so you have, and the equivalent linear solution is to replace the slope of that bilinear model by an equivalent modulus, GEQ, which the last lecture called the secant modulus. And then to take the area of the loop and based on that develop the energy dissipated per cycle, which then represents the viscous damping. So then instead of looking at following the loop, you replace it by two parameters, the slope of the loop and the area of the loop, the secant modulus and the damping value. And the analyses I went through to compare the equivalent linear and nonlinear was to look as shaking was going on, how that loop was evolving during shaking using the bilinear solution, and then by replacing each with its equivalent value, came up with the equivalent secant modulus and equivalent damping. And then when you compare the two solutions, this is the velocity spectrum using a bilinear solution compared to that using the equivalent linear bilinear acceleration spectrum. And you can see there, in those days, I don't know why I should have really plotted these, but I don't have the actual numbers and I didn't want to go digitize them. I just copied them out of my paper we published in 1968, actually. And but when you make a comparison, they're pretty close to each other. So on that basis, then concluded that we can use the equivalent linear solution as a reasonable representation of the real nonlinear behavior with the intermediate step of using a bilinear solution. So then what was going on in the 60s was research at the University of Michigan under the leadership of Professor Richard, totally independently whatever we were doing at the University of California at Berkeley, carried out comprehensive testing program to measure modulus and damping values. They showed dependence of these values on amplitude of vibration. They didn't look at strain, they looked at the amplitude. So I took all their work and converted it to strain and found exactly what I found from when I examined Terzaghi's data. So really then became a whole set. And because of that, I think we all changed to using strain rather than amplitude. This work was initiated in the early 1960s. And then the late Professor Seed and I began to compile the dynamic laboratory test on SANS, mostly from the University of Michigan, which included free vibrations and resonant column test. This effort began in 1968 and culminated in the preparation of this report and the introducing of the concept of G over G max. And I was very happy to see that being used in static analyses in the last presentation. And this report was published by ERC in 1970. And for those of you who publish papers and sometimes get it rejected, what I want to tell you about this report is we actually wrote it as a UC Berkeley research report. Then we sent it to ASCE for possible publication in the journal of, at that time it's called Soil Mechanics and Foundation Engineering. It was rejected. And we didn't fight it, so we just kept quiet and said people will either use it or not use it. But I think it's probably one of the most cited reports even today. And that's what 70 today, is that 50 years ago, is still being referenced. So don't give up if you get rejected from publication. Another example, about 2 years later, we also sent a paper where we looked at what happened in San Francisco in 1957. It was a very nice paper. We submitted to the Journal of Structural Engineering at the ASCE. It was also rejected. This time I said to Professor Seed, we have to fight. We can't let 2 for 2. So we did fight, and it was published. and actually received a very high award from ASCE, the second highest award. So again, if you get a paper rejected, don't give up. Just keep at it. And this is now the figure that we generated. This is G over G max as a function of strain and the range that, personally, if anybody wants to use this, I prefer to use the upper line. And now since then, of course, a huge amount of work has been going on and still going on and will continue to go on. And there are a multitude of figures that are available. Example of G over G max published over the years. I have the list in here, but I usually cover it. So I'm not trying to push anybody or to say anything about anybody's work in particular, but you can see this is depending on the type of material, whether it's sand or clay, depending on the confinement. And again, I was very pleased to see that for the static stress, the last presentation was using G over P prime. So that was very, very, very consistent with what we've been seeing in the dynamic analyses. Now, one thing that I've also seen in practice that is of concern. Some people take what they measure in the laboratory and what they measure in the field. Now, in the field, what we measure using downhole measurements or the OYO technique, which measures incrementally, or surface wave analyses to get the shear wave velocity, which is the G0 or G max at very low strains. And then we take a sample and take it to the laboratory and test it. We will never get the same value for G max. But what we've come up with and is to look at the lab data and get the G over G max from the lab data, and then up the curve to meet the shear wave velocity we measured in the field. Because that is a correct value. It has no effect of disturbance, sampling, method of testing. Well, it does affect on method of testing because there's variation in which method we use, but at least it is the best measure we have for what the real maximum shear wave, the maximum shear wave velocity or the maximum shear modulus. So please, if you ever do that, use the lab data to get the G over G max, but make sure you pin it to what you measure in the field. I have seen some applications, especially in clays, where people ignore what they measured for shear wave velocity in the field, but take only the lab and keep the lab data as being the correct ones, which are typically, in terms of actual numbers, about a half or maybe 40% of what you measure in the field in terms of G max. And if that clay layer is in the middle of a profile, it acts like a base isolator and reduces the output above it. So please be careful with that. So the continuing our activities in the late 60s and early 1970s, analyses of shaking table tests on earth slopes suggested the need to have an ability to use different damping values in various parts of the slope and to develop. And the development of a variable damping finite element method was necessary, which later was named a quad 4. And that means because before that we were using the same value, the same damping value throughout the profile or throughout the dam. And what that suggested is that we should vary that, and we had to do that by changing the program. And then Dr. Schnabel came to Berkeley as a young graduate student, started research using the finite element program developed in 1969, initiating comparisons using a continuous solution to check accuracy. Both approaches, the time domain finite element, which is the quad 4, and the frequency domain continuous formulation, introduce high damping. Well, because and that was why what limited actually acceptance of what Professor Kanai had suggested. Is you just take the wave propagation, the continuous solution of wave propagation as it existed, will automatically highly damp the higher frequency and therefore kill really the high frequency content. independent of any analysis they do. So when Schnabel and I discussed this issue with Professor Leismer, who had up to that time concentrated on working on foundation vibration issues, he suggested a novel approach to overcome this issue. And I think this effect had a profound influence in how things advanced in terms of looking at site response. Professor Leismer suggested that the viscosity coefficient in the complex modulus expression be replaced by the damping ratio, because by keeping that viscosity coefficient a constant, you're automatically saying that the damping ratio will increase with the frequency. But all our test results suggest there is no dependence of damping ratio on frequency. So what Professor Leismer, the late Professor Leismer, unfortunately, suggested is to change the viscosity value in the expression in the equations to the damping ratio. So now you're making the damping ratio constant, but the viscosity coefficient is decreasing with frequency. So, but that doesn't affect the results like the damping ratio does, thus making the damping ratio frequency independent as it should be. So now with all these introductions, then came up with a program Shake, and that led to development of other programs that expanded into finite element to 2 and 3 2 dimensions, and eventually, no, actually only 2 dimensions. So now let's look at site response analyses. A large number of recordings were obtained at many sites during the Loma Prieta earthquake. Many of these sites were in the San Francisco Bay Area, including sites at Treasure Island. So what I'm going to look at now is looking at these various procedures that we have available to us. And these include equivalent linear and nonlinear procedures. These are the only 2 really. But within the equivalent linear procedure, there is a time domain way to go at it, or the frequency domain. The frequency domain is what we mostly shake, and it's whatever spread out of that. And basically, they all do exactly the same thing, but working in this frequency domain. There's a Rascal, there's ProShake, and there is ABC, whatever. Many of them, but they're all basically the same. In the time domain, we have the quad 4, which could be used either for 1 or 2 dimensions. We have now deep soil can do that, and but deep soil can do both equivalent. I mean, does equivalent linear as well as nonlinear. For nonlinear programs, we have deep soil for them available to us to use, which is a program developed at the University of Illinois, and of course the program FLAC. There is a program in finite, and FLAC is a finite difference solution. There are nonlinear finite element programs that can, but have yet to really gain in the nonlinear arena to gain the popularity or the usefulness or the expansion that FLAC has, the finite difference technique. So what I'm going to do is look at these things in this sequence. So first of all, I'm going to look at the equivalent linear solution. Again, I'm looking at the Treasure Island site, and the Treasure Island is here's San Francisco, Oakland, Berkeley, the Bay Bridge, and Treasure Island is San Francisco. Treasure Island should be right off the Bay Bridge, right this little green stick. If I remove the pointer, you'll see Treasure Island. And when I look at the details, here's Treasure Island, and there's another island that connects to it. It's called Yerba Buena Island, and there was a recording at the ground surface at Treasure Island right here, and a recording at the ground surface at the Yerba Buena Island. This is close, which is really a rock site at Yerba Buena Island and a soil site at Treasure Island. And there were many other recordings during the Loma Prieta earthquake, quite a few of them on soil sites as well as rock sites, and we'll look at that a little later. So here's where we have recordings at Treasure Island, which is the soil site, then Yerba Buena Island, the rock site, and all of these are the other rock sites, 2 in the one in Berkeley and one in Piedmont, which is really the heart of Oakland, and seven in San Francisco. So 7 plus 2 is 9, and 1 is 10. So we had 10 recordings on rock and 1 on soil that we're going to examine. So first, let's take a look at Treasure Island. Basically, it looks a sand fill over the Young Bay mud, over the older sand, and then very old clay, and then some sand all the way down to the Franciscan Formation, which is a weathered rock. And eventually we get to shear wave velocity of about 1,800 meters per second. So that's a pretty good rock actually at that depth. And we have shear wave measurements, and the shear wave measurements at about that depth is about 1,100, but it goes out to about 18, somewhere in this vicinity, about 1,800, 2,000 meters per second, depending on which procedure was used to measure these shear wave velocities. So now we have the recordings on point C, which is Yerba Buena Island, and we have a recording at Treasure Island, which is point A, if you recall the figures I've been talking about. So this is how we simplified the profile, and this is what was recorded. The Treasure Island site is the black one, and Yerba Buena Island site is the blue one. So then our input, point C, what we get from C is the blue one, and A is the black one. So now if we go through and calculate using shape, without going into the details what went into that, this is what we get, the red line, which captures the essence. It does not capture everything correctly. It captures the peak acceleration is pretty close. The peaks are obtained. This not that well, but these two are reasonably well. And now we vary the properties quite a bit, and they do change the results. Again, the dark black one is the recording, the blue one is the input, which is the C, which was modified to become B to put at the bottom of the profile to get the red and the other dashed blue black lines. But you can see that the effect of varying properties quite a bit did not have that much effect on the response. All of them basically gave the same thing. The acceleration was affected the most, but the ground acceleration, but the spectral values themselves were not. And what's really intriguing is to see how little difference in terms of the shape of the spectrum was affected over here. Now, since we have these other 9 recordings, well, the question is, why not use one of the others, and how well would that do? And that really was a very important thing to have done, because when we do that, we find that while we get this with Yerba Buena Island input, this is what we get when we add the other 9. Absolutely none of them would fit the observed values correctly, anywhere near correctly. You can see the green lines are all over the place. So what tells us then is that the input has a huge influence on site response. And we can just arbitrarily select an input. And since 99.9% of the time we don't know what the input should be, we have a target spectrum we can get, but then we need a time history to put into the system. And there's so many ways we can generate a time history that if we just depend on only one, we could be this green line in a comparative way, or the red line, or this green line. So we could be either pretty close to what is a reasonable comparison of reality, and reality being what was recorded, or far away from it. So we have to be very careful in doing it. So the best way to do that, overcome that, of course, when we don't have a recording nearby, like we had in this case at Yerba Buena Island. There's another site, by the way, the San Francisco site, where we have also a companion recording not very far away on a rock, got exactly the same conclusion. With that input, it came out doing well. With all the other inputs, it was not that good a comparison. So what it means that for future application, we should never, ever rely on one analysis, no matter how good we feel about it. We should, in my mind, we should use at least 7 to maybe 9 or even 13 But we're still looking at that. Fortunately, we haven't had time to look at this as carefully as I'd like to. But at least we know that this should be at least 7. I know many analyses that do 3, which is better than 1, but not as good as 7 or 9. So now let's look at the downhole array. After the Loma Prieta earthquake, the state of California went in and put in 1, 2, 3, 4, 5 instruments, downhole array right next to the Yerba Buena, the Treasure Island site. And we had some very small earthquakes, the largest like magnitude 4. So levels of shaking were not very high. And we went through some analyses and we got reasonable results, but I just don't have time to do that. So the next thing I want to do is just how well these various programs compare. First, looking at the equivalent linear, looking at shake, which is one frequency domain solution, and looking at the deep soil, which is a time domain solution using equivalent linear, and then looking at the nonlinear solution, deep soil and flak. So first, let's look at the using the equivalent linear solution using deep soil. This is what you get, and it's very comparable to what we had gotten with shake before. When you make the comparison, actually, they're almost identical. They differ a little bit, but they're almost identical. Now we look at the nonlinear deep soil. It does a pretty good job as well. It suppresses these values because typically nonlinear solutions that have a small component of Rayleigh damping, and Rayleigh damping has a feature of overdamping higher frequencies, suppress some of these frequencies, as you can see here. So be careful when using a deep soil type analysis that you look at what's happening at the higher frequencies and maybe in your mind apply a judgment factor. They should be a little higher because they were somewhat depressed. And you can see that here, very clearly what's happening. It didn't affect the values at this or here. These are the lower modes or the higher period, longer period, lower frequencies. But I keep going in the wrong direction. But it did affect the higher frequencies. So keep that in mind as you go through, if you use these programs. The next thing is to look at what flak would do, and flak, I went into a little more detail. By the variety of ways you can apply, define the soil properties and which stress-strain relationship or model you want to use. You can use Moore Coulomb, you can use hysteretic model, you can use the these most recently developed PM4 sand or PM4 for the sands and PM4 silt for the clay. So we went through some of these results. If we take flak and use the hysteretic model for the Young Bay mud, we get these results. Again, we're capturing the peaks, location of the peaks extremely well, but really overdoing it somewhat. Not quite, at this location quite a bit. It's more than double. If we change from the hysteretic model to PM4 silt, actually we get the best comparison almost from any model with this, especially at these two peaks. It's a little bit overestimating here, but that's from about 17% to 20, not quite 21% G. So it's not as bad. At now, so you can see that we can get reasonable results using any of these programs as long as we use the correct properties. And also keeping in mind that whatever procedure we use has its limitations and has its uncertainties. And that's where really experience and judgment have to enter into the picture. So let's look at the spectral shape, see how different these results are. This is the recording. Now change the spectral shape. And my apologies, by the way, what you have in your package does not show this ratio, shows spectral value. It should have been divided. divided by PGA, but that's okay. These are correct. The spectra had been divided by the peak acceleration, and therefore this value is 1. So that was the recording. And this is the 2 FLAC models. Whether we use hysteretic or PM4 silt, the spectral shape doesn't change. The actual numbers change. There's a little bit of a difference here, but the spectral shapes are almost identical. When you add to that the deep soil nonlinear, it's also very comparable, or almost identical, in fact. So in other words, what's happening at the frequencies is not affected much by which procedure we use or which assumption we use on these properties, but the actual numbers themselves are. Now, you do notice here that the hysteretic model and the deep soil both eat a little bit of this higher frequency, which is what PM4 silt does not do. And now we add shake, and again, it fits together. So altogether, I think they give about, and here's the comparison with the actual recording. And you can see now we do have this little peep in here, and it's captured by the FLAC with PM4 silt, and the rest do not capture it as well. So overall, then, I think we all do a reasonable job, as I said before, but please be careful in interpreting and in making judgment on what to do with it. Finally, one of the nicest things about the development of these models, PM4 silt and PM4 sand, is they allow us to look at the evolution of pore water pressure in the system. And I'm just going to look at a very simple solution here for at Treasure Island by looking at the evolution of pore pressures in the sand layer and in the clay layer. Now, if you're working on a dam, that could be a very important thing, or working on one where the level of shaking is much higher and you're getting close to liquefaction, or in the case of clay, to cyclic softening to the point where you might cause failure. These become very important. None of the other programs do this. Certainly the equivalent linear programs do not do this at all. Deep soil has a component to it that allows for looking at excess pore water pressure. And when I was working with Dr. Hashash and his students back in late 2018, I sort of became a student to understand how that works so I can use it. And I spent 3 times 1 week each time to being a student at the university, and it was very enjoyable and very delightful experience. And I really thank Professor Hashash and his students for giving me that opportunity. And this reminds me of a poem I think Robert Frost is reputed to have written, which says basically that the older I get, the younger are my teachers. And sure enough, on understanding deep soil, that was the case. I did spend 3 wonderful weeks at the University of Illinois, appreciating that. Plus, to do FLAC, Katerina at the University of California at Davis was my teacher, and she's a fabulous teacher. So I thank all of them. So let's look at the development of this pore pressure. The use of PM4 sand in the sand layers and PM4 silt for the Young Bay mud provides the means to calculate the excess pore water pressure induced in these layers during shaking, as we're going to illustrate at these 2 depths. So if we look now at what we're doing at the clay at this depth and the sand at this depth, this is roughly for about 8.5 meters, about 20 some odd meters. Feet, meters. When we look at the sand, this is the acceleration at that depth, roughly at that depth. We don't have the exact depth because when you calculate pore pressure, it's in between 2 nodal points. So you sort of split the difference. So you take the acceleration above or below that. And this is the pore pressure at that depth of 8.5 meters. And you can see that for this particular earthquake in the sand layer, there was very little pore pressure developed. But you can see it revolve. Had we had a much higher input, I'm sure this would have been up high and probably reached liquefaction. When we look at the clay, we can see that this is now a depth of 21 meters, the acceleration, and the pore pressure at 20.5 meters. You can see the pore pressure was getting to be fairly much larger, to about 20%. Again, the level of shaking is not that high. Otherwise, this would have been much higher. But what's intriguing here is there was a buildup, and then as shaking was continuing and the level of shaking was reducing, the pore pressure began to dissipate. Of course, the permeability is not that high, so it wouldn't dissipate as fast. We don't have that information on the sand because the level is so low that we can't tell how fast it would, but it also would dissipate there as well. That's the value of these models, which are really very powerful and very useful models. I've been seeing them now being used on tens of applications. I'm involved in several projects right now. Tailings dams, sites for waste disposal, waste treatment plant in Vancouver. All these models are being used very successfully. So they're very good. So some concluding remarks. The equivalent linear procedure has been and continues to be widely used procedure in practice for calculating site response and for developing site-specific earthquake ground motions and design parameters. And it has also been widely used for evaluating existing and new earth structures and for assessing SSI aspects. Now, I know many people think that why are we still using equivalent linear when we have these fantastic nonlinear programs, which are far closer to what reality is. But what's useful about keeping equivalent linear solution alive, so to speak, is that it provides a sanity check. And because nonlinear programs can get very complicated and the black box gets bigger and bigger and bigger. It's big enough in the equivalent linear, but trust me, it gets really huge as you keep putting things into that black box. So having an equivalent, a simpler solution, where you know that at somewhat reasonable level of shaking, you can get reasonably accurate or reasonably reliable results. You can see what these bigger black boxes give you and get a sanity check on that. So I know I've been at it for 60 some odd years, so I won't be around that much longer. But I hope that all you guys in the future will always keep that in mind, not only for these types of problems, for every problem we face in geotechnical engineering, because we always need that sanity check. Let's not go for our computational capability has advanced so rapidly and so hugely that sometimes we forget that we have to stop and make a sanity check. I hope we always do that. Continuing with our concluding remarks, advances in nonlinear analyses are encouraging, and the results presented today highlight the values of using such analyses. Care must be exercised selecting appropriate constitutive models for the various soil layers comprising the profile under consideration. Calibration of the selected constitutive model with relevant test data and empirical correlations is essential. Professor Hashash and his collaborators have done that for the model built into deep soil. Professors Boulanger and Ziotopoulou, they are the ones who created the PM4 silt and PM4 sand, and their collaborators have done that extensively with PM4 sand and are continually adding to that effort for PM4 silt. Now, I wrote this about 1.5 years ago, and I'm continuously involved in projects where their updated models are being used, and sure enough, they are updating them, and there have been some very significant improvements. So please make sure you use the latest, so to speak. The results for the Treasure Island site using PM4 silt for the Young Bay mud highlight the importance of accounting for pore water generation and cyclic softening during shaking. So the key factors that affect the site response calculations are: the input motion can have a profound influence on calculated site response, as evidenced from the results shown earlier for the Treasure Island site. The soil profile also will influence the calculated site response. The soil properties also influence, but to a lesser degree than input motion or soil profile. The method of analysis will influence the results depending on the level of shaking on the selection of parameters. For the Treasure Island site, the effect was minimal for the level of shaking experienced in the Loma Prieta earthquake. So please keep that in mind. So now I'm a couple please. Please limit the use of equivalent linear procedures to those in which the calculated effective strain is less than about 0.6%, which means the maximum strain is less than 1%. And this is a very important thing to keep in mind. The equivalent linear solution is based on replacing the correct nonlinear stress-strain relationship by rays of secant moduli. And you get to about 1% strain, actually 0.6% for the equivalence of the max, because we always look at the uniform strain rather than the maximum value itself. So at about 0.6%, it's getting pretty flat. And you saw that in the G over G max or the G over P prime, G0 over P prime that we saw in the previous presentation. So when you get beyond that, it gets so flat that you basically are softening the system so much, the results are really meaningless. Because equivalent linear solution use only a single number. They're not like the nonlinear solution where you can build up, go from a high modulus to a lower, 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 lower as you're going along the stress strain curve. So you can't make that jump from all the way to 2 or 3% strain where the modulus will be practically nothing, very, very small. So please be sure and if you see any analysis where people have gone beyond 1% maximum strain, do not accept it. It is, in my mind, it's a piece of junk. So we're not going into deconvolution, so I won't say anything about that. And then allow for variations in shear wave velocities and in modulus reduction and damping curve within physically meaningful ranges. The reason I say this will become evident shortly, because I've seen now so many people invoking these random realizations, and they allow the model to go berserk. And that's a very technical word, berserk, by allowing values that could never be at that particular site. If you have a dense sand and you drop in the shear wave velocity to like 50 meters per second at a depth of 30 meters or so, that's an impossibility. So please be sure that you don't allow that. So when using a randomizing process to allow variations in these properties, be sure to check that any realization is physically meaningful. Casagrande, who gave the second Terzaghi lecture, the mine is number 55. So that's 53 years ago. Actually, more than that. It must have missed some years. I think he gave his in 1966 or 67. Casagrande in his Terzaghi lecture number 2 emphasized the need to select probable range of pertinent soil properties guided by judgment and experience. This is a valuable and timeless advice. We should all heed it. And finally, Confucius said, life is really simple, but we insist on making it complicated. Look at all the stuff I've been talking about in the last hour or so, or what we heard in the previous hour. But Einstein said, everything should be made as simple as possible, but no simpler. So we have to work in between the two. Finally, I want to really thank my family for the continuing love, support, and tolerance over all these years and all of ups and downs every one of us goes through. And I am eternally grateful to so many very talented friends and colleagues. When I gave the lecture in Philadelphia, I went through a list of some 30, maybe more individuals. I won't do that now because I'm sure Professor Briaud wants me to stop. But I'll just mention a few names. Among these, of course, would be the late and only Professor Seed, Harry Bolton Seed, as you see him in the literature. He was my mentor, my friend, and my esteemed colleague. And since then, of course, I've been working with Professor Boulanger, a delight to work with, and Katrina Zilotopolo, she's a delight, and Professor Hashash, and it, my gosh, I shouldn't start, I will never stop. So, and of course, I've had some very wonderful colleagues and clients on various projects for the past 30 plus years. I thank you all, and I thank all of you for listening to this. And if you see my email in my presentation, if you have any questions, please email me, and I do my best to respond to you as quickly and as effectively as possible. Again, thank you, Professor Briaud, for asking me to represent this. I've represented it a few places. I always use different words in between, but the gist of the lecture is the same. And I wish we were doing this in person. I would have loved to break bread with you and drink some wonderful wine. Thank you all, and let's hope we all stay safe and be careful. Thank you very much.
Thank you so much, Professor Idriss, for this excellent lecture and some of your philosophical thoughts as well. Geotechnical earthquake engineering is not a simple field, but us on that journey, starting with the very simple concepts all the way to the complex problems. You're not only a very talented geotechnical engineer, but also a great teacher.
Thank you.
Your review of the history of how the field evolved and your conclusions and final recommendations were particularly precious. It's my pleasure to give you a certificate to thank you for sharing your Terzaghi lecture with us. It will be in the mail very soon. Thank you again for a great lecture.
Thank you very much.
This concludes.
We have we lost a lot. We only have 100 people.
This concludes the Buchanan and Terzaghi lectures. I wish everybody good health. See you again soon.
Okay, arrivederci.
Bye-bye.
Stay safe.